In this video, we're going to be talking about a part of probability theory that's given rise to its own branch of statistics called Bayes' rule. And Bayes' rule states that if we're given K mutually exclusive meaning that they can't overlap at all in our probability space, and if they're also exhaustive, events, and we're going to label those events B1, B2, and all the way up to BK, such that the sum of their probabilities is equal to 1. So we have probability of B1 plus the probability of B2 plus all the other probabilities up to the probability of BK is equal to 1. And we know that this must be the case since we have these K events that are mutually exclusive, meaning they can't overlap at all, and they fill up our entire probability space. So if we add up all their probabilities, it has to sum to 1. If we then also have an observed event, A, which can overlap any number of these B events, but has to still be in our same probability space, then we know that the probability of B sub I given A is equal to the probability of B sub I intersect A divided by the probability of A. And we can use our conditional probability rule to expand out these formulas. So we're going to do that. We're going to get the probability of B sub I times the probability of A given B sub I divided by the probability of B1 times the probability of A given B1 plus the probability of B2 times the probability of A given B2 plus all the way up to the probability of BK times the probability of A given BK. So this rule doesn't seem very naturally intuitive, so let's go over an example to kind of understand what this really means. So for our example, we're going to say that we have a new software package that can classify people as cheaters or not cheaters for writing a given paper. So we're going to say that people are cheaters or not cheaters. And from our survey results, we know that 10% of the time people are cheating and that 90% of the time people are not cheating. And our system is going to give us positive results and negative results, basically trying to tell us whether or not we think that someone is cheating or not. And we know that if someone is cheating, which is 10% of the time, that we will get a positive result 90% of the time. So this is 90%, which means that we get a negative result 10% of the time. Then we also have, if someone is not cheating, we get a positive result, so we're wrong 15% of the time. And we get a negative result, or we're right 85% of the time. So that means if we want to try to label our data points here, we have a true positive if we have a positive result when someone's actually cheating, and we have a true negative when someone is not cheating and we get a negative result, which means that these last two are incorrect, which means that this first one up here, so when not cheating and a positive, is a false positive. And when they are cheating and they get a negative result, it's a false negative. So to look at what our table is actually trying to tell us though, it's telling us that when someone is cheating, so we have the probability that when someone is cheating, so when they're a cheater, we get a positive outcome 90% of the time. But that's not the information that we actually really care about as an educator. What we really want to know is what is the probability that someone is a cheater given that they got a positive result. So we're going to use Bayes' theorem to figure out what the differences are in those two very similar seeming questions. So again, what we're trying to figure out is the probability that someone is a cheater given that they got a positive outcome. So given this formula here, we know that we can break down this conditional probability equation into a fraction where we have the probability that someone is a cheater and, so the intersection, that they got a positive result, divided by the probability that they got a positive result. And we know from the multiplicative rule of probability that we can break down this top part of our equation in two different ways. So we can say that this is equal to the probability that they got a positive result multiplied by the probability that they are a cheater given they got a positive result divided by our same probability of a positive result. Or we can break it down and say what's the probability that someone is a cheater times the probability that they got a positive result given they're a cheater divided by the probability of a positive result. So if we look at these two equations, now which one is more useful to us? So if we look at the top one, we have probability of positive times probability of cheater given positive divided by the probability of positive. But if we want to simplify that, we would actually cross off the bottom because it matches part of the top of our equation. So we'd have the probability of positive cancels out probability of positive, which means we're just left with probability of cheater given positive, which brings us full circle back to our original question. That means we're going to be stuck with this bottom one. So what we're going to need to figure out is we're going to need to figure out the probability that someone is a cheater. We're also going to need to know the probability that someone gets a positive result given they're a cheater. And we need to know the probability that someone gets a positive result. So again, what we're getting is the probability that someone is a cheater times the probability that someone got a positive result given they're a cheater divided by the probability that someone got a positive result. So to figure out all these different values, we actually need to walk through and fill in part of the rest of our table. And to do that, what we're going to do is just multiply these two percentages together. So when someone is a cheater and they had a positive outcome, what's the percentage of the total population that that makes up? So we know that cheaters are 10% and positive outcomes are 90% times that 10%. So we're going to get 10% times 90, which is going to give us just 9%. And we just walk through and do this for the rest of our table. So we have 10% and 10%. So we have 10% times 10%, which is just going to give us 1%. We have 15 times 90, which is going to give us 13.5%. And we have 85 times 90, which is going to give us 76.5%. So what these values are really telling us is they're telling us what's the probability that someone is a cheater and positive, or what's the probability that someone is a cheater and negative, and so on for the rest of our table. So we can use this to figure out the different probabilities that we need. So to figure out the probability that someone got a positive result, we can just add up the row for positive results. So we have the probability that someone is a cheater and got a positive result, which is 9%. So we have 9% plus the probability that someone got a positive result and is not a cheater, which is 13.5%. We know the probability that someone is a cheater, which is just that 10% that we were given before, or we can walk down our column and add the 9% and the 1%. So we're going to say 10% for someone being a cheater. And now we need to know what the probability that someone got a positive result is given that they're a cheater. And we know what this value is equal to the probability that someone has a positive result and that they're a cheater divided by the probability that they're a cheater. So we know that these values are equal to, we have a probability that someone's positive result and a cheater, which is our 9%. and we have the probability that someone is a cheater, which is our 10%. So when we fill in our values for our function, we get this is equal to the probability that someone is a cheater, so we have our 10%, times the probability that someone got a positive result given they're a cheater, so we know that that is 9% divided by 10%, divided by the total percentage of people that got a positive result, which is our 9% plus our 13.5%, which is equal to 22.5%. So we'll put 22.5% down here. And if we see this, on the top of our fraction, we can simplify a little bit. We have our 10% and our 10%, which actually will cancel. So we got our 10% canceling our 10%. So we're just going to get what is 9% divided by 22.5%, which is equal to 40%. So that means that given that someone got a positive result, 40% of the time they're a cheater, which means that 60% of the time we're getting a false positive result. So from a system developer perspective, I might need to go back and retune my system to get a better result, since over half the time when I give a positive result, or over half the time when I think someone is cheating, they're actually not cheating and I'm misclassifying them. So some poor student is going to be misclassified and called a cheater when they're actually not cheating on their assignment.